Good evening, students, faculty, alumni, and friends. I'm Neva Spake, Dean of the College of Arts and Sciences at Appalachian State University, and I welcome you to the inaugural Mountain Studies Lecture. This lecture is a signature event and recognizes the wide variety of research, scholarship, and instruction that occurs across our college related to mountain studies. In 2019, Dr. Baker Perry, a professor in our Department of Geography and Planning, collaborated with a team of scientists, experts, and local Sherpas on the National Geographic expedition to Mount Everest called the 2019 National Geographic and Rolex Expedition to Mount Everest. This expedition will help define our understanding of high mountain environments and learn how climate change is impacting Mount Everest itself. Joining Dr. Perry on this expedition and also contributing to this evening's program were Dr. Anton Simon, Research Assistant Professor in Department of Geography and Planning, Dr. Tracy Simon, Dr. Aurora Elmore, Alex Tate, and Dr. Paul Majewski. I thank them all for contributing to this lecture and for their commitment to science. I would also like to recognize and thank Dr. Saskia van de Gevel, Chair of the Department of Geography and Planning, for moderating tonight's question and answer session with the scientists, and Ellen Burnett, the college's Director of Marketing, Communication, and Engagement, for producing this evening's program. Finally, I'd also like to thank Dr. Catherine Ledford and her working group who organized the Mountain Studies Symposium in 2019 that helped plant the seed for this new lecture series. As extraordinary as the expedition to Mount Everest is, I would also like to recognize our longstanding collaborative efforts between the National Geographic Society and Appalachian State University. For more than 20 years, numerous faculty have worked with the National Geographic on a variety of projects to study, for example, methods of teaching geography to school-aged children, mass extinction, early Homo sapiens in Africa, and the responses of plants here in Appalachian to the ozone levels. I would also like to recognize and commend Drs. Cynthia Lucas Pierce, Larry Kimball, Howard Newfield, James Young, Sarah Carmichael, and Saskia van de Gevel for their work with the National Geographics over the years. In recognition of our institution's past collaboration and ongoing partnerships, I would like to present this gift as a token of our appreciation to the National Geographic Society for their friendship, support, and collaboration with our faculty and by extension, our students. We hope that tonight's program inspires new and innovative ideas for sustained collaboration. And now on to our program, which will highlight the biology, the geology, and meteorology research efforts that were integral part of the larger 2019 Everest expedition. For this evening's event, we are calling it Reaching New Heights, highlights from the most comprehensive science expedition to Mount Everest in history.
Thank you very much, Dean Spake, for that kind introduction, and for your generous gift highlighting some of the wonderful Appalachian State University projects that National Geographic has supported over the years. I am Dr. Aurora Elmore, Senior Program Manager at National Geographic Society. It is my pleasure to join you all today on behalf of National Geographic to kick off the inaugural Mountain Studies Lecture at Appalachian State. I'd also like to thank Dr. Saskia van der Gevel for facilitating today's discussion, and Ellen Burnett, Mark Bradbury, and Baker Perry for organizing this historic event. I'll begin the lecture series today by introducing Paul Majewski, Director of the Climate Change Institute at the University of Maine, who was the expedition and science leader for the 2019 National Geographic and Rolex Perpetual Planet Everest expedition. Here's Paul with a message from the Khumbu region of Nepal on the importance of high mountain glaciers and their role providing water resources for 1/5 of global population.
My name is Paul Majewski. I'm the Director of the Climate Change Institute at the University of Maine, and I'm sitting on a stone wall in Phortsi in Nepal, and more specifically in the Himalayas, very, very close to Ama Dablam and Mount Everest, spectacular mountains that everybody knows about. These mountains are part of the Himalayas, and the Himalayas have tens of thousands of glaciers, and those glaciers are critically important to 20% of the world's population. Whether or not those glaciers get bigger or smaller is extremely important to agriculture, ecosystem and human health, the potential for flooding, a variety of other things. A fantastic report just came out by ICIMOD. It's a non-governmental organization in Nepal, and they've summarized in a fantastic way all of the information about this particular region, the Khumbu Himalaya. And they talk about how the fact that the glaciers have gotten smaller over the last 10 to 20 years. They talk about many of the implications of this decrease in the size of the glaciers. But one of the things that's particularly important is this part of a natural cycle or not. And in Greenland, about 20 years ago, we collected a record using an ice core, a cylinder that goes back in time, that goes back year by year, 110,000 years. And we were able, with that record, to see natural cycles in the climate. And what is happening today is absolutely not part of a natural cycle. We are seeing an increase in warming that is much faster. We're seeing a change in the chemistry of the atmosphere that is unparalleled in 100,000, and I can say easily even a million years, if not Earth history. All of these dramatic and fast changes are critically important to places like the Himalayas, because the Himalayas are an important water tower for, as I mentioned earlier, 20% of the world's population. When you think about that, 20% of the world's population totally dependent on the amount of water that comes into this region. If there's too much water, because the glaciers are melting too fast, there's an immense amount of flooding. If there is too little water, then agriculture begins to fail. And over time, we will most likely, unfortunately, see melting accelerating, which means more flooding, unless we have some mitigation tools to deal with this. And we will, as a consequence of, in time, having less and less glacier volume, therefore less and less water availability, we'll see these regions having potentially more trouble with agriculture, and we'll also see these regions having a harder time utilizing hydropower and hydroelectric power. And hydroelectric power, as I've learned on the way up here, we're at about 3,800 meters, serves about 90% of the total energy for the people in this region, with 10% being the other, in solar being the other part. So this is a very important place to study. ICIMOD has done a fantastic job organizing all of this information, and there's a lot more that we need to do to understand how fast this change can be in the future and what the impacts of this change are going to be.
Thank you, Paul, for illustrating the many important reasons why it's critical to gain a better understanding of alpine glacial systems, especially in the high Himalayas. Despite the need for more information about alpine climate change, there's a distinct lack of scientific data available from the highest reaches of our planet. That is something we are working to change. Today's discussion stemmed from the 2019 National Geographic and Rolex Perpetual Planet Everest expedition. As Dean Spake mentioned earlier, this was the most comprehensive expedition to ever research Mount Everest, known locally as Sagarmatha and Chomolungma. During this expedition, 34-member science team spent almost 2 months in the Khumbu region of Nepal examining how climate change is affecting the highest mountains on Earth. There were 5 scientific teams, including the geology team, who aimed to understand how the region had changed in the past, and the glaciology team, who collected the highest ice core in the world. Today you'll be hearing from the other 3 teams, biology, mapping, and meteorology. None of this work would have been possible without strong support from the people of the Khumbu region and our world-class Sherpa climbing team. Today's presentations will include interviews on high alpine biology with Dr. Tracy Simon from the Wildlife Conservation Society, who was co-lead of the biology team, and Appalachian State's own Dr. Anton Simon. You'll also hear about mapping the world's highest glacier, the Khumbu Glacier, from Alex Tate, the geographer at National Geographic. Finally, you'll hear from Appalachian State professor Dr. Baker Perry, who co-led the meteorology team for the 2019 Everest expedition. Baker and his co-lead, Dr. Tom Matthews from Loughborough University in England, worked with a phenomenal team of elite Sherpa climbers to set up the highest weather station that has ever been installed on the planet. Before each of these interviews, you'll see some wonderful videos from the National Geographic Impact Media team. I invite you to learn more about this record-breaking expedition, as well as see some live data from the world's highest weather stations at natgeo.com/Everest. And now, let's kick the event off with the first video titled Life is on the Rise about our biology team, which will be followed by a personal question and answer session with team members and Appalachian State University's Saskia Vandegevel. Enjoy.
Comparing it to historical data from previous expeditions can give us a lot of information about whether we can actually define how quickly these species are already moving upwards.
The two types of surveys we'll be doing are water filtration, collecting water samples, doing things like turning over rocks, looking underneath and seeing what's there.
As a biologist, I focus in on the micro scale to really look for minute little details. It's great working with Anton as a partner because he can step back and look at it from a more holistic understanding.
I've got a background looking at the climatology of landscapes, and so that helps us understand better the organisms that we're studying in the context of the landscape. In terms of the ability to respond to climatic changes, different species have different capacities for response. To use a local example, purebred yaks can no longer live at the elevation where they used to live.
My whole family has lived in these mountains their whole life. They have seen changes themselves and they've lived through changes. Before we could see yaks down to Namche, but now they are no longer able to tolerate the warming climate here, so they have to move about. These small, minute observations are actually very much important for any sort of scientific-based understanding.
When we come up here to do our visual encounter surveys, we'll pick a piece of habitat that looks really good for species. The soil will be well developed, there'll be plants. We'll turn over rocks.
Oh, that's a bristletail.
Bristletail.
Got him.
You got him.
And when we find something, we'll collect the animal in a plastic tube so we can photograph and measure it and document it.
He's got these long elements sticking out.
The slope is incredibly unstable, rocks constantly in motion, and there are pebbles and rocks covering the surface, but when you remove them, look underneath, we're finding that basically soils are developed. There's mosses, there's little tussock grasses. Basically, an ecosystem seems to actually be developing under the surface of this very unstable, rocky substrate. And there's much more life up here than meets the eye at first glance, that's for sure.
When we get back to the lab, we'll do analysis combined with reaching out to local experts like entomologists and botanists to be able to identify all the species at the taxonomic level. If there are any microorganisms in here, they'll be throughout the solution.
Oh, something moving.
What we're trying to do is gather as much information as possible to really understand how can we adapt to climate change? How can people adapt to living up here? How are species adapting? This climate change study doesn't end here. As scientists, we want to provide the impetus so that these studies can continue on for years to come, so that people can have a better understanding of what's happening and how to adapt as we move forward.
Hi, Tracy and Anton. This is Saskia Vandegevel from the Department of Geography and Planning at Appalachian State University.
Hi, it's great to be here.
Great to be here. I'm Tracy Simon. I'm the director of the molecular laboratory for the Wildlife Conservation Society. I'm based at the Bronx Zoo in New York.
And I'm Anton Simon. I'm a research assistant professor in the Department of Geography and RIEEE at Appalachian State. Been affiliated with the department for 8 years, though I work remotely from New York here, upstate New York with Tracy. I also am rostered with National Geographic as an explorer, because I've got a long-standing 20-year relationship with the organization, which has been quite terrific. That's a point of entry for how we ended up on Mount Everest.
Well, that is a great introduction, and it leads us to our first question from a student asking, why did you decide to focus on an alpine environment for your work?
This goes back to my PhD work, which is sad to say 20 years ago now. I was doing a PhD in the University of Colorado, and I kept going down to the Andes, backpacking, adventuring, and doing that kind of stuff. And down in South America there, I was seeing fascinating stuff in the very high mountain environments. And it seemed to be a manifestation of the impacts of climate change in these very pristine areas. And if you really want to understand climate change in the present day, not as something just a problem for the future, you want to put your finger on the pulse and go and find a living laboratory where you can actually see changes in progress. There are two places in the world that we knew of where you'd already see this: is the high Arctic and tropical high mountains. So that's what took us to tropical high mountains. And actually it's through this pathway that Tracy and I began working together as well. She leading biological programs and me looking more at the physical science and climatology of climate change in these environments.
That's great. Tracy, I know one of the things you're most excited to talk about is the eDNA work that you've found there and how it can be used to assess alpine biodiversity. Could you tell us more about that?
Yeah, so eDNA, it's environmental DNA. And this is DNA that's shed from organisms that exist in the environment. And so you can kind of think of it, if you go swimming in a pond, you're shedding cells off into that pond constantly while you're swimming. And I could go in, take a liter of water, and actually test if you've been swimming in that pond. So it's used as a forensic tool to look for rare and threatened species, but we can also use it to perform biodiversity surveys to assess the breadth of biodiversities in environments. So on Mount Everest, we used eDNA to assess the biodiversity and took water samples from different ponds at increasing elevation. So we'd capture 1 liter of water in duplicate samples. We'd filter it on site and capture the DNA in these little filters that have really, really tiny pores that allow the water to flow through, but it captures the DNA. And then we take that and we sequence the DNA to assess all the different species that exist in that sample. And by doing that, we can look for not just the big animals like the dogs and the snow leopards, but we can also look at invertebrates like mayflies and dragonflies completely across the tree of life, going all the way down to bacteria and viruses. And so what we were hoping is to create a baseline to assess, what are the organisms that live up in these high alpine environments? Because only a small amount of scientists actually venture into these high elevation sites to perform field work. And so we wanted to comprehensively examine what species live up there so that we can compare it both to past and look to see if there's been changes occurring over time.
And if I could take a step back actually as to how we actually came to be on Mount Everest, with Tracy sort of leading this very pioneering biological survey up there in eDNA. It goes back to the roots of the work I've been doing for years down there with Baker Perry and Appalachian State students now, going back more than a decade, where we keep going back to the same field areas in Peru and Bolivia. And we're researching and studying and monitoring changes that are going on. We do have citizen scientist initiatives there where they help collect data for us and inform us on the changes that they're seeing in the environment. Meanwhile, Tracy has been working with other biologists and ecologists and botanists within our framework, our research framework, to also be monitoring things, but now looking at the biotic component, actually to see how the biosphere itself, the living life zone on Earth, in this case, it's the upper reaches of the Amazon ecosystem, itself is rising to occupy space that used to be filled with ice and snow. As deglaciation has continued, we're getting these very dynamic changes, and we can go year to year, keep going back to the same places and monitor the rates of change. So Tracy led an initiative first looking at amphibians, now it's spread to vegetation and various other, all different life forms. And it's that background, which was cultivated from my time working with the partners here at Appalachian State and many South American partners, that then it resulted in us being invited to go to Mount Everest to do very similar types of work now in the framework of this enormous National Geographic expedition with more than 40 scientists. And
That really is amazing that long-term connection has gotten you to do this work today and look at these elevational gradients and biodiversity. With that in mind, how have these geographic ranges of some of these species, whether they're bacteria or viruses or invertebrates, how have they changed with increasing temperatures?
Well, if you take, for example, some of the species we've been studying in the high Andes, which we have the most data for going back year after year, what we're finding, for example, with amphibians, which are a great indicator species because they're very sensitive to environmental change. What we're finding is that glaciers are receding and new ponds are forming and frogs are expanding their range upward and occupying this new habitat that's developing at the wake of these receding glaciers. So we can actually quantify how fast are these frogs moving up. And then also, because they're being impacted by this infectious disease, chytrid, we can monitor how the fungus, the chytrid fungus, is impacting them as they're adapting and moving around to these changes. And the dynamics are really quite striking. So new ponds are forming while other ones are drying up because they're no longer fed from the glacier. So we're seeing really dynamic changes in amphibian distributions up in these high mountain environments. And so we're following that and monitoring it over longer periods to better understand what the impact that's going to have on the ecosystem and that species.
Well, thank you both so much. I know that we all enjoyed watching your video of the research you're doing. And we really appreciate you explaining eDNA to us and the importance of biodiversity at such high elevations and the importance in our lives. Thank you both.
It's been a pleasure.
Yeah, pleasure.
Thank you much.
Mount Everest has been on the map since the mid-19th century, but it wasn't until about the 1920s when the British first started sending expeditions to the north side of Mount Everest through Tibet that we got large-scale, detailed mapping. They were doing all their surveying using photographs and telescopic instruments to tie things together on a topographic map. The transition from maps as paper products to maps as digital products has changed the way we work with geographic data. We're going to reconstruct how the glaciers have changed with the increased warming of the climate in this part of the world. The big questions this expedition is answering is how climate change is happening in the high mountain regions. Maps are a critical tool for being able to measure the changes in the glacial extent. When we came over the crest of the hill and took a look at base camp the first time, I was like, oh my God, I can't believe we're going to be trying to map this.
So at this angle, are we going to have to?
Correct. Yeah.
Whoa.
Crazy. That's a big one.
One of the many avalanches every day.
People understand Everest as this big, beautiful mountain with a huge glacier running down it. If that glacier is gone, that's something that can't be brought back.
As the glaciers melt, there's an initial increase in the amount of water available, and then eventually a decrease in the amount of water available to the rivers that come out of high mountain Asia. Hundreds of millions of people are going to be affected downstream. The Khumbu Glacier is the highest glacier in the world. It starts at about 8,000 meters on Mount Everest and what's called the accumulation zone. It's where all the snow falls and starts compressing into ice and flowing downhill. Base Camp, it's a launching point for expeditions and climbers that are intending to summit Mount Everest. We wanted to map the full extent of that, to capture the physical information, but also to better understand how climate is modifying the glacier. The work that Chris and I are doing here at Base Camp will be the most detailed map of the Khumbu Glacier that's ever been put together. The equipment that Chris and I are using is a very recently developed terrestrial-based LiDAR system. We're combining that with our helicopter-based LiDAR scanning, using a very advanced device from Virtual Wonders, our partners on the helicopter scan.
The tools that we use for the terrestrial mapping are really threefold. We're using LiDAR, which is a laser scanning tool. It shoots out 2 million points per second, taking individual measurements in a 360-degree sphere and measures everything that it can see. If you do that in enough places, you build an overall topographical model of whatever it is you're scanning.
Base Camp is about 3 kilometers from one end to the other and a couple hundred meters wide. And it took us many stations to be able to collect all the data that we needed for all the tent areas and the glacial areas that are used for Base Camp. Once you create a 3D model, you then need to what's called skin the model with very detailed imagery.
We take pictures using DSLR photography. We're going to take high-resolution images to paste onto those measurements that the laser scanning provides. So right now I'm taking 3 frames at a time, 2-stop exposure bracket. We have bright snow and really dark shadows. We need to be able to capture all of that information. If we were to lose highlights or lose shadows when we're building that environment that the model's going to go into, we just don't have that data. We're never capturing it again.
So we're doing our first overview pass with the drone, so flying at about 50 meters. It'll fill any gaps that we might miss with a LiDAR and with ground-based photographic work.
This is a really difficult environment. Drones really help us give the overall perspective on Everest Base Camp. And the last thing that we're doing is taking a helicopter and attaching a LiDAR system and a video camera and flying it up and down the Khumbu in a gridded pattern so that they can create a map of a much greater scale.
The combination on the helicopter of the very advanced LiDAR and the photogrammetry will allow us to provide very detailed imagery on the surface of the model. Once we're back in the lab, we can see all the different LiDAR data collected in one view. We've done a very, very detailed map of the Khumbu Glacier. This is Base Camp. The entirety of what you're seeing here is computer generated. Once you get the full resolution of the photography, it's going to be a virtual reality experience, as if you were there looking at the tents at Base Camp. So if we take our 3D model, we can dive into it and start looking at more and more of the detail that's captured by the point cloud. What we're going to be able to do is take this data and reconstruct how the glaciers have changed. One of the things that you can notice, the Khumbu Glacier has receded. It's probably dropped tens of meters in its elevation, so that it's had an ice loss that's really pronounced for such a short time period. This is a global issue that's going to have global ramifications. Every person in the world will be affected by this. One of the goals is to not just generate new science, but to have the chance to build on the legacy of mapping this area, to instill in people how important climate change is, and to start working on addressing it now for a successful future.
Hi, Alex. Thanks so much for joining us today. My name is Saskia Van de Gevel, and I'm the chair of Geography and Planning at Appalachian State University, and I'm interviewing Alex Tate, the geographer for the National Geographic Society. Thanks so much for answering some of our really important questions about Everest and the work you did with cartography and remote sensing on the mountain.
Thanks, I'm glad to be here.
Well, our first question from one of our students is, how does this mapping work and virtual reconstruction fit into the historical record of mapping Everest?
So the data we collected and the work we did really follows on some amazing work that's been done over the past almost 100 years of mapping Everest, starting with the British expeditions in the 1920s, going through the first successful ascent in the 1950s, and some important work that was done by Brad Washburn from the Boston Museum of Science and National Geographic in the 1980s. And each of these time points, there were aerial photographs and maps created. And the work we did sort of allows us to compare present day, or 2019 when we collected the data and did the mapping, with these past time points to look at changes in the glacier, both in the volume of the glaciers and the extent, but also in the surface cover and some of the other aspects of the high mountain environment that are revealed by the high-res imagery.
Wow, what were the oldest maps that you had and oldest aerial photography?
So the oldest maps that are really, usable topographic reference are from the 1920s, when the British expeditions first went to mostly on the north side of Everest, but they also peeked over into the south side where we were doing our mapping in the Khumbu. So that was done in the 1920s, some very detailed topographic maps with the technology of that era. The first flight over Everest was in 1933, and they captured amazing aerial photography, not for mapping. They were actually producing a film and sort of doing the first flight over Everest, but some of those photos are usable as reference for changes in the glacier. The first real combination of high-res aerial imagery and topographic mapping was from the 1950s by an Austrian named Erwin Schneider. And so we used the 1950s as a starting point for looking at some of the glacier change. We worked with a group from St. Andrews University, and a paper is coming out soon about the glacial change. And for the entire Khumbu region around Everest, we're able to look back to the 1950s for parts of the area, but really the 1960s, when the first satellite images were collected of this area, spy satellites that the US had put up, the Corona and Hexagon satellite imagery. So we can use that and see how much the glaciers have receded and how much volume has been lost at different time points, including the 1980s, the 1990s, and the 2000s, to compare to today.
That's amazing that you have this 70-year record with aerial photos or more, and then it's over 60-year record of remote sense images too. That's amazing. Yeah. And it leads into the next question, which is, what evidence of human activity and occupation did you find while mapping? So what's our human footprint on Everest?
So that, of course, that human footprint is at several different scales. You can, of course, obviously look at the scale of the entire glacial mass in high mountain Asia and in the Khumbu region around Everest and see the recession of the glaciers, which are related to climate change. But on a much larger scale, finer scale, you can see we did our imagery during the climbing season in 2019. So you can see all the camps and you can see what the footprint of 1,000 people at Everest Base Camp is, all the tents. It's a tent city. And there's some modification of the glacial surface itself by the climbers and their teams when they establish base camp. We also get a good view of Camp 2 at about 6,300 meters up in the Western Khum. And of course, we can also see human evidence down the Khumbu Valley, where the trekking villages of Gorak Shep and Lobuche and Tukla are, and you can see all the trekking, the footprint of the trekking industry. Of course, we have a resident population that's farming and raising animals, yaks. So you can see the patterns of grazing. So our biology teammates were looking at some of the grazing and the distribution of the plants and the botany around the Khumbu Glacier. So there's a lot of evidence of different types of human impact that we can see in the imagery.
Yeah. And then our last question is, how do we use this virtual reconstruction to encourage people around the world to recognize the magnitude and impact of climate change and the importance of acting now, especially with these alpine glaciers?
So as you've seen in the video, the impact of being able to recreate the mountain environment in a virtual way allows us to give people a feeling for what it's like. You can combine the photographs and the video imagery from the cameras on the helicopter, but it also, the virtual reconstruction via the LiDAR and the imagery into a 3D world on the computer allows you to bring people into the environment in the high mountains without them being there. And so you can show glacial change, you can show the human impact. It allows us to reach out to people and engage them in a different way than a science paper would, for example. And of course, that's one of the things that National Geographic has always done. And working with our museum team, there's going to be an Everest exhibit in the museum that's going to be using this data that we collected, anything from a physical model to virtual reality goggles to bring people into the high mountain environment. And hopefully they can get an appreciation that there are people that make their living there through the tourism industry, and how important this high mountain environment is and how it's being impacted by climate change. These people have to adapt, both farming and tourism. All of these important economic activities for the residents of the high mountain Asia region are impacted by climate change.
Well, thank you so much for combining storytelling and science to really bring us the story and bring it into our homes, because so few of us will ever be able to make it to Everest, but to feel like we're there is incredible. And I really want to thank you for that.
Great. I'm glad that we're able to do that. And it was really the trip of a lifetime for me as a cartographer.
Thank you, Alex.
Thanks.
Everest is one of the most extreme environments on the planet, and nobody has ever fully quantified the climate conditions up there. We're going to be pushing the envelope, attempting to install the highest weather station in the world to improve our understanding of weather patterns and climate change in the Mount Everest region. These high mountain regions are changing faster than other places around the world. The highest elevations are actually believed to be warming at faster rates than other lower elevation regions. My major role in this expedition is to install a network of weather stations, including what we hope to be the highest weather station in the world.
We're here installing the lowest of our network of weather stations. Firstly, to transmit the data, we require quite a lot of power. If the system doesn't have enough power, it will refuse to transmit data. That would mean we couldn't see what was going on in real time, which is what we really want. We want to know in real time what's going on the mountain. The weather station sees a whole year's worth of weather possibilities, measuring wind speed, thermal radiation, temperature, humidity, and precipitation. We can use machine learning to provide a totally different approach to how you can forecast weather. We are filling in gaps in how the climate is changing.
There are multiple stations going up, including one at Fort Say, one station at Base Camp, one in Camp 2, another at the South Col, and then we will attempt to install one above 8,000 meters.
Let's face it, climbing Everest is still a very difficult thing to do. It takes years of time developing the skills, the confidence, the ability to deal with a constantly changing mountain environment, to deal with the cold, to deal with the high altitude. And you can't fake it.
Pretty snug, but not so snug that I'm pushing really hard against my face.
Okay. And then just set your reducer right on top, and then you're going to be spinning the bottle counterclockwise.
This morning we have installed what we call the Base Camp Rover. It's critical to have a station here on the glacier to be able to observe and to measure the meteorological processes. We've got electronics that need to operate at extreme temperatures, exceptionally high wind speeds. Having instruments that can work in those sorts of environments has been a big challenge.
And that plane's good, so yeah, tighten everything. You say? Can you test this out? Yes. Good man.
There's a reason that some of this has never been done before. Logistically, it's exceptionally challenging. It's physically demanding in and of itself just to climb and function up at 8,000 meters. To try to do science up at some of these elevations is an added challenge. I think people are feeling as good as we can at this stage of the expedition, and we're excited to move up to Camp 2.
As a scientist, we're used to having to be patient with things, and this expedition has been no different. It's been nothing but eat, sleep, think Everest for the last 9 months.
Camp 2 station is in.
This environment is uncontrollable. It's hostile. It doesn't care whether we're successful on our expedition, and we have to be prepared to deal with that as best as possible.
It's about 10:45 p.m. I'd be lying if I said I wasn't a bit nervous. I am. I know how big the challenge is ahead, and I feel very confident in our team. We know that we may be limited by the weather, so we're going to try and get up there just as the sun is rising when the winds are lowest. We have maximum for oxygen about 3 hours to install the station. We need to be efficient and work as a team.
Here's the balcony. We're going to my valve. I'm not getting enough air in. I have to lift my gas like this. Putting with the batteries. Too close to work. Yeah, we fan it, the batteries fan it, so I just have to wait.
I'm a bit worried that we won't be able to think clearly. We may make a mistake that means we leave those stations in a position that's suboptimal, that they're not transmitting.
And we try to warm up the down jackets, stuff under armpits. The sun's about to come up, we can help a bit too.
My fear is I won't know my limitation, that all their efforts for nothing. It's about being resilient in the face of a mountain that really doesn't care about you.
Temperature? Yeah, it's good. No other wind.
It's a rare opportunity to come here and do a scientific expedition like this.
This is the highest weather station in the world.
That gives us information to plan for future scenarios of climate change.
We got SkyTrack now to Washington, D.C. Undoubtedly the highest that's been installed the Dalkany, Everest. Thanks to Tom and all the Sherpa colleagues. Doing such a great job.
Hi, I'm Saskia Van de Gevel, the chair of the Department of Geography and Planning at Appalachian State University.
And I'm Baker Perry. I'm a professor in the Department of Geography and Planning at Appalachian State University.
Thanks so much for joining us today, Baker. And it was really exciting to see your video and the work you were doing on Everest. One of the students had a question about, in the video you say that it is physically demanding to function at 8,000 meters. Can you describe what it actually feels like to be at that altitude?
Well, first of all, thank you for hosting us. This is exciting to be able to share some of the research and the expedition itself. And functioning up at 8,000 meters, which is just over 26,000 feet. I mean, I think it's important to keep in mind that this is the elevation that commercial jetliners frequently cruise at. And it's literally on the edge of the world. And number one, it's very cold up there. I mean, we spent 2 nights at that elevation and the better part of a day and a half. And the temperatures range between 0 and negative 20 degrees Fahrenheit. Okay, so I mean, we're walking around in down suits, which are, you know, not much better than a sleeping bag, and so they're very bulky. We have big boots on that are very warm and well insulated, but they're heavy, they're bulky, they take a lot of time to put on, and so just dressing for the cold is a major challenge. We've got big mittens, big gloves, and of course the wind is also blowing a lot of this time, and so the wind chills were frequently down negative 40, negative 50 degrees Fahrenheit below zero, and so that was one of the major challenges. The second major challenge, of course, was the lack of oxygen, and so we're in an environment where there's approximately a third of the oxygen that's available at sea level. And so we were, you know, our team was using supplemental oxygen, but even with that, there are major challenges, and just motor function is reduced. The brain does not work as well. And every little effort, just taking a step and just bending down to get something off the ground is a major effort. And it was just exceptionally difficult to even just be awake and function. And a lot of our time in preparation for moving higher out of the South Col was spent also in melting snow. And we had stoves that, because there's limited oxygen up there, they don't work as well. And it takes a lot of time just melting snow and preparing meals to rehydrate and getting stuff packed for our next climb. And so just everything about life up at these elevations is exceptionally challenging. And that's certainly one reason why a lot of this scientific work that our expedition accomplished was just not possible or had not been done previously.
That makes sense. And, you know, with that in mind, with that energy level and with that exhaustion and that body stress, thinking of the equipment, what special considerations were made in the design of these high elevation weather stations that aren't used to being at such a high elevation?
Yeah, so one of the major challenges early on in the design of the weather stations was how to balance lightweight, because they had to be light enough to be carried up by a team of Sherpas, and but yet they needed to be strong enough to withstand 200 plus mile an hour winds, icing, and even small rocks and pebbles picked up and thrown at the station itself. And so that was the fundamental design challenge from the beginning. And so we ended up with a design that we used aluminum for the tripod, and we've got the weight of the tripod down considerably. And there's only so much we could do with the batteries and the sensors and the data loggers and the cases that they all had to go in. And so the total weather station ended up weighing just over 100 pounds. And so, even with it being as light as we could manufacture those components, this was still a substantial load that was distributed over about 5 different people from our Sherpa team. And so that was, of course, one of the major challenges, balancing the lightweight capability and the strength. We also had to make sure the sensors that we picked were tested and could function at these sorts of temperatures and at these pressures. And so we did some special characterization and testing of these sensors. Wherever possible, we also used redundant sensors. So for wind speed and for temperature, we installed 2 sensors actually, in case one failed. We still had a backup. And then the batteries were specially engineered to work in very cold environments as well. And then, an important consideration too is that everything had to be have the capability to be put together very quickly, because we had a limited window up there, especially for the highest station at the balcony, because of limited oxygen and just the weather conditions, and everything had to be put together, assembled in a very short time. We were planning on an hour and a half or so to complete the installation. Now, compare that to kind of normal conventional installations, which can go on easily for several days. This was a major challenge that we had to have things that could be put together very quickly, also with gloved or mitten hands, so we weren't prepared or expected to have any dexterity in our fingers. And so this was a major challenge that our colleagues at Campbell Scientific helped with. We tested in Nepal earlier in the year with the Sherpa team in January. We tested on Mount Washington, in the White Mountains of New Hampshire. And when we got back to Nepal and base camp in particular, we went through multiple scenarios of installing the tripod, drilling the holes, and then setting the anchor bolts in rock. And so our Sherpa team was incredibly fast and quick learners in this process, and we had rehearsed this pretty reliably from the beginning. Okay. The other thing I will mention that we did, the data logger, the computer, the brains of the weather station, utilizes smart programming so that when battery power drops below a certain threshold, the station does not try to send the data over the satellite telemetry link. All right. And so that has really, I think, extended the operation and the battery life of the station, and ensured that data continues to be collected even in times that the battery voltage gets a little lower. So data collection was a priority over sending the real-time data via the satellite, and so that will allow the station to last a little bit longer too.
So then how does the data that's locally recorded that may not be sent, How do you collect that? And also tied into that, what are some of the more major findings you've had from this data that you've received so far?
Right. So eventually, when the satellite telemetry comes back online and we're able to transmit the data should catch up. Okay, they should eventually be transmitted. Now, in the event that that does not happen, or something knocks out the satellite communications, the telemetry completely, data are also being recorded on a flash card and on the memory of the data logger. And so in that case, if someone goes back, it's possible to retrieve the data directly from the weather station. And so that's been, so far, it's a setup that's worked pretty well from what we can tell. And of course, there's always the chance that a sensor will be damaged or somehow fail. And on the lower stations at Fort Say, in the community of Fort Say, and at Base Camp, those two stations are readily accessible throughout the year. And it is possible to get someone from our Sherpa team up there to have a look, even up to Base Camp if conditions warrant. But above that, at Camp 2 in South Call on the balcony, it's really nearly impossible to get up there, except for during that main period of April and May in the climbing season. And of course, in 2020, nobody went up there because the pandemic had just started, and the climbing season on Everest was completely canceled. And so those upper stations are very, very challenging to maintain. And we hope that a window will open in April and May of 2021, this coming spring, that will allow us to go and have a look at the stations and see what repairs and maintenance needs to be done on them. Now, in terms of the major findings, these weather stations have provided a window into the highest reaches of the planet that we just never had before. And one of the really interesting findings early on that we saw from especially Camp 2, South Call, and then we can infer that some of the same processes are occurring up on the balcony, is that the incoming solar radiation, the energy from the sun, is just incredibly high up there. I mean, we're seeing incoming values of solar radiation that are higher than what we would expect at the top of the atmosphere. And we believe that's the case because there's a lot of fresh snow and ice and clouds as well. And so there's multiple pathways coming in that can increase the solar radiation. And that means that there's actually more energy available for melt up there than what we had realized previously. And so that is a significant finding because even though temperatures are well below freezing up there with the very intense solar radiation, that can still lead to surface melting and maybe playing a role in some of the observed deglaciation that we're seeing across the Himalaya and the high mountain Asia region. We also have measured some incredible wind speeds up there. In fact, our South Call station measured a gust to 148 miles per hour last winter. And so we know that this is an exceptionally windy place, and the stations are positioned right there in the subtropical jet stream. And there's very few places on Earth that actually have the capability to have direct surface measurements of the jet stream. So that's a really important feature that we will continue to monitor. We have already demonstrated that we can improve weather forecasts on the mountain as a result of the data that we are collecting. And in particular with temperature and wind speeds, we have demonstrated improvement on the model forecasts, which are fairly good, but there's always room for improvement. And so having 1 year of measurements has demonstrated that we have that capability to improve the forecast, and that should translate into better climbing forecasts during the main climbing season in 2021 and beyond. And then we've also been able to look at the sources of moisture for precipitation events in the Everest region using our really the whole network of weather stations. And from that work, we have shown that the Bay of Bengal is the primary moisture source for the snow that falls on the Khumbu Glacier, the highest glacier in the world, and that there are some other sources just in the interior of India and also the Northern Arabian Sea and the Indus River Delta that are also important. But the bulk of the moisture appears to be coming from the Bay of Bengal for these precipitation events.
That's really exciting that you're able to capture all this information in such a short amount of time since setting up the stations to really get that umbrella view of all the different kinds of research applications. I know you mentioned earlier the important role of the Sherpas, and I wanted to ask you how critical in the success of the expedition were they, and can you elaborate on their major contributions?
Our Sherpa team was absolutely critical in everything we did up there, from the climbing to the scientific work. And it's just not possible to do anything up there without the help of the Sherpas. I mean, they are the ones that set up the camps for us, that transport the heavy gear, the tents, the oxygen up high. They did multiple carries up over 26,000 feet. And as I mentioned earlier, they did a lot of training on how to set up the tripods, how to drill into the rock, and how to install the sensors on these stations. And so without them, there's no way we could have done any of this work. And I just want to be crystal clear that they were absolutely exceptional. And this begins with our lead Sherpa, Panuru, who has 14 Everest summits under his belt. And he was the one entrusted with our safety as well, and did everything under his power, under his leadership to make sure that we all stayed safe, that we met the goals of the scientific mission, and that we all returned safely. And I mean, the Sherpas have been doing this in their backyard their whole lives. And so they are uniquely adapted to function in these exceptional altitudes. And not only from a physiological perspective, but just from a, just a broader perspective. They were just a total pleasure to work with. And it's really important that we express the gratitude that we are for their huge role in this expedition.
Well, thank you so much, Baker, for sharing your experience and for also speaking about your research and speaking about the role of the Sherpas. We really appreciate your time today. And thanks for giving us a little bit more insight into what it feels like to be on Everest.
Thank you, Saskia.
Namaste, my name is Panu Sherpa. So last year, 2019, I am a National Geography Everest expedition for weather stations. I'm climbing Nepalese climbing Sherpas leaders. So I have experience like how to sit in the weather station in the mountain. There is I'm going also this year, 2020. Namaste, thank you.
Namaste, I am Patashi Sherpa. Last year I've been net geo expedition in Everest. I've been the weather station team, and that time I have little bit understand the weather station.
Namaste, my name is Pinju Sherpa. I live in Fort Say. So I joined National Geographic expedition last year, and there's the 100% successful for weather station in ice core. I'm working with Mario in ice core. So we check the ice core, Lobuche Summit, and Everest Base Camp, and Camp 2, Camp 1, and South Col, above South Col in the ice field. There's the 8,000 meter. There's the we take up the ice from there. There's the, I think 100% success. That time is a very good weather and very good ice condition, and everybody safe. And this next day we have to go up to balcony. Also, there's 8,400 meter. There's the, we set up the weather station. This weather station is very really good working. It's the everybody have a safer, and now in the Khumbu Valley and everywhere watching the National Geographic weather station. There's the one of the high point weather station. That's the very nice one, and this is the working. And maybe I hopefully I'm joined with National Geographic expedition this time also. Thank you very much.
Namaste, my name is Pasankami. No English, sorry.
Namaste, my name is Tenji Gyalchen Sherpa. I'm from Forje. Last year, I am Nature Group. And thank you.
Namaste, my name is Nimarita Sherpa. I'm from Forje. Namaste to all. This is me, Tenji Gyalchen Sherpa from Forje. Last year, I involved with the National Geographic team as well as base camp manager. But this year, I am helping for the climbing crew, and I'm very happy to visit on the highest weather station around the balcony. I hope maybe in the future we can set up on the summit of the Everest, and this is very helpful for all around the world. Most of the now, all the climbers are very they are searching on the net geo weather station, and they are very accurate weather in the Khumbu Valley, and that's very useful for us. And happy to work together. Thank you.
Namaste everybody, I'm Lakpa Gyalchen Sherpa from Forche. Last year I've been working for National Geography expedition, and last year I was the part of weather station team, and we have successfully set the weather station in Camp 2, South Col and Balcony. It was a great success, and hopefully maybe higher than Balcony this coming year.